Welcome everyone. In this video, what we're going to do is we're going to take a look at VSEPR structure, and we're going to distinguish between what is an electron geometry versus a molecular geometry. We're going to start by discussing electron geometry. You see, the electron geometry has to do with the total number of domains surrounding a central atom. When I say domains, a domain can have one of two things. An atom can be connected to another atom, which we would call a bonding domain, or instead of it being connected to an actual atom, there could be an unshared pair of electrons, which we call lone pairs, and that would be another type of domain that you might encounter. So if you look at this slide here, when you have a central atom with two domains, you'll see that the electron geometry is called linear. If it has three domains, it's known as trigonal planar. And if it has four domains, you'll see it's known as tetrahedral. The word tetra means four. So let's take a look at this a little bit more closely. So here we have three pictures. The first one has two domains. Notice it has an electron geometry known as linear, and you'll see that the angle is 180 degrees between those two atoms that are bonded to the central atom. In the next figure, you see it has three domains, and you'll notice this one's called trigonal planar. Notice the angle between the atoms is 120 degrees. And then when you have the tetrahedral electron geometry, you'll notice there's four domains, and the angle there is 109.5 degrees. So if you look here, we're going to also look at two other domains. There is one that has five domains, and that electron geometry is known as Trigonal Bipyramidal. And then we have another final structure that has six domains, and it's known as Octahedral. And these two domains, in order for them to exist, the central atom would require it to be an element that can hold more than 8 valence electrons. Therefore, that atom must be in the third period or beyond. That atom would be an exception to the octet rule. Now, here's what we're going to do. We're going to look at them a little bit more closely. And here you have the picture of the trigonal bipyramidal with the five domains. Notice this one has two possible angles. The first one is from the top atom here to one of the three on the sides. Notice this angle here is 90 degrees. Okay? But there's another angle. You see the atoms in the center, they kind of form a triangle. And if you look at it, if you look at this triangle, from one to the other, towards the middle, you'll see that they make 120 degrees. So the 90 degrees is from the top to one of the ones in the middle there. And then if you do the angle from one of the middle ones to one of the middle ones, it kind of looks like a propeller. You'll notice that that angle is different. That one is 120 degrees. So trigonal bipyramidal, there are two angles there. Now the octahedral, notice that you have six domains, and they're all 90 degrees, okay? The one from the top to the bottom would be 180, but they're all 90 degrees to each other, okay? So here's what we're going to do. Let's take a look at them individually. Let's go back to the first shape with two domains. We know that the shape is called linear. That's the electron geometry. And both of them have to be atoms. A domain where it's a physical atom connected to the central atom is called a bonding domain. A non-bonding domain would be a lone pair. So for linear, the only possibility is that both are atoms connected to the central atom. So it has two bonding domains, and there are no lone pairs. And an example would be carbon dioxide. You could see it over here. And of course, the angle to this is 180 degrees. Now, look what happens when we go to three domains. Well, if all three domains are atoms, which we would call bonding, if it has three bonding domains and no lone pairs, the molecular geometry, which would be actually the shape that we name the molecule, the molecular shape, would also be called trigonal planar. Okay, so notice that, and we can go back to the previous one, the electron geometry and the molecular geometry both go by the same name. They're both linear. Well, with trigonal planar, if all three are bonding domains, the molecular geometry is also called trigonal planar. However, here's an example where you have three domains and two of them are atoms and one is a lone pair. And you could see the example here. Okay, you'll notice that you have nitrogen has three domains around it. Two of them are oxygen atoms. Those are your two bonding domains. And then you see a lone pair at the top. That's your non-bonding domain. And when you look at this, the molecular geometry has a new name. We don't call it trigonal planar. It has an electron geometry of trigonal planar because it has three domains. But the breakdown is two bonding and one non-bonding. So we give it a new name for its molecular geometry. We call it bent. And you could see that with trigonal planar, we said the angle is 120. When it's bent with this one lone pair, the angle is actually going to be slightly less than 120 degrees. The lone pair kind of like squeezes the angle and makes it a little smaller than 120. And you can see this would be the general formula, okay, of a bent structure. It has three domains, so it's trigonal planar as far as electron geometry, but the molecular geometry is bent. Now we're going to take a look at something that has four domains. So if you look here, tetrahedral is that there are four total domains. Now, if all four are bonding and none are non-bonding, as you can see here with CH4, which is methane, that electron geometry and the molecular geometry share the same name. They're both called tetrahedral. And the angle is 109.5 degrees. Now, let's look at an example. If you have four domains and three of those domains are atoms or bonding domains and one is a non-bonding, the E here is for electron pair or lone pair, you're going to see that the molecular geometry will acquire a new name. I'm going to show you now. It's called Trigonal Pyramidal. Sometimes you'll see it just called Pyramidal, depending on the textbooks. But if you look here, notice that ammonia, three of the four domains are bonding. You see three H's, but there's a lone pair. In other words, there's a non-bonding domain. So even though it has a tetrahedral electron geometry, the molecular geometry acquires a new name. It's called trigonal pyramid or pyramidal. And the angle, again, because of that lone pair squeezing the atoms a little tighter, it's going to actually be slightly less than 109.5. In fact, the angle in ammonia has been measured to be about 107 degrees. Now let's take a look at one more example. How about if you have four domains and two of them are bonding and two are lone pairs? The fact it has four domains still makes it tetrahedral. However, the molecular geometry will acquire a new name. It's going to be called bent. So if you look here, if two domains are bonding, and water is a perfect example of this, you have two bonding domains. Each hydrogen is a bonding domain, and you have two lone pairs. So again, it has four domains, so it's still tetrahedral as far as electron geometry, but the molecular geometry is called bent. And again, it's still going to be the angle less than 109.5. In fact, the measured angle of water is about 105 degrees, which is less than 109.5. So notice we have two different structures called bent. We saw earlier that we have a bent that has one lone pair that had an electron geometry of trigonal planar. It looked kind of like this, where you had a central atom and then you had two atoms on the side here like this with one lone pair. And then you have water, which has also two bonding atoms, but it has two lone pairs. The difference is that this one over here has a trigonal planar electron geometry. This one has a tetrahedral electron geometry, although they are both called bent as far as their molecular geometry. Now we're going to look at something that has five bonding pairs. If you look here, okay, if you have five domains, you're known as trigonal bipyramidal. If all five are bonding and none are non-bonding, then you retain the trigonal bipyramidal name. And remember, this one had two angles. We talked about how it could be either 90 degrees or 120, depending on which atoms you're looking at. And this first one here is simply, I'm not going to draw the lone pairs around the chlorines. They each have 6 dots around them, but you'll notice there are 5 domains around the phosphorus, okay, and that is trigonal bipyramidal. Now let's take a look at this. Going back to this one here, if 4 of the domains, okay, are, and I'll use this structure here. I'll draw 4 domains here like this, and then I'll draw an E for an electron pair. This one has 5 domains, but if you look carefully, 4 are bonding, and you can see it over here, and 1 is non-bonding. Okay, here's an actual example. I'll show you that one in a moment. You'll see that it acquires a new molecular geometry. It's known as seesaw. Okay, the example that was listed was SF4, and when you draw that, it'll look something like this. Each fluorine, I'll put the lone pair here, each fluorine will have, its characteristic lone pairs. So I'm actually drawing this one accurately, and you can see that it has 5 domains, but out of the 5, 4 are bonding, 1 is non-bonding, so it has the seesaw name. But you also have some other combinations. You have one called T-shape, and if you look at this one has 3 bonding and 2 non-bonding. When I draw this, it would look something like this. The fluorines would be here on the side, okay? And it has actually 2 lone pairs, like this. The central atom, the chlorine, has 5 domains. 3 of them are bonding, the 3 fluorines, and then 2 non-bonding. Notice it has 2 lone pairs around the chlorine. And it's T-shaped because it kind of has this T-looking structure here. That's where the name comes from. Now, you also have a linear that is a trigonal bipyramidal electron geometry. If you look at this example here, you'll notice that when this one is drawn correctly, it's going to look like this, and the xenon in the center here will have 3 lone pairs. So it'll have 2 bonding domains, which are the fluorines, and then 3 non-bonding, which are the 3 lone pairs. And it's linear because you can see the structure is straight. This one's actually 180 degrees. And this one, even though it has a trigonal bipyramidal electron geometry, the molecular geometry is called linear. Okay? Now we're going to take a look at the octahedral. Here's an example of one of them, but let's look at the original one. If you have 6 domains, you're octahedral. If all 6 are bonding, okay, and no lone pairs, then the molecular geometry is also called octahedral, and you have SF6 would be a perfect example. You would have, these right here like this, sulfur hexafluoride, just like that, okay? The fluorines would each have 6 dots around them, but notice sulfur is an atom that's disobeying the octet rule, has an expanded octet, but that doesn't matter because sulfur is in the 3rd period and it can do that. Now, look at this next one called square pyramidal. Okay, if you look over here, actually that's square planar. Let's go back to square pyramidal. If you have 5 out of the 6 domains are bonding, and one is non-bonding, and I'll go ahead and draw this one here. You have 5 fluorines. There's 1, there's 2, there's 3, there's 4, there's 5 here, and there's a lone pair. Notice there are 6 domains, and I'll do this one more accurately. Notice that out of the 6 domains, 5 of them are occupied by fluorines, those are 5 bonding domains, and then there is 1 lone pair surrounding the BR in the center. There's your non-bonding domain. So this one here is known as square pyramidal as far as the molecular geometry. Remember that octahedral, the angle is 90 degrees. But we also have one more structure here where it's a 4-2 breakdown where you have 4 bonding and 2 non-bonding. I'll come back here and show you this one. This one's known as square planar, and the general formula looks like this. So you'll see the central atom, you'll see the peripheral elements, and the central atom will have 2 sets of lone pairs. Notice it has 4 bonding, 1, 2, 3, 4, and 2 electron pairs or non-bonding, but there's 6 domains, so it's still octahedral, but the molecular geometry is square planar. The example shown here is xenon with 4 fluorines, and you'll notice I've used xenon a couple times in examples. Xenon is a noble gas, so the fact I've used these as examples, these are man-made compounds. Anytime you see noble gases in a compound, that's not natural. They need to be forced to react. So this is a man-made compound here, because you don't see xenon or any other noble gases for that matter pretty much in a bond. They don't react. So notice this one is square planar. The electron geometry is octahedral, but the molecular geometry is square planar. So there you have the octahedral ones. So let's take a look here at a couple of examples that we can do here. Let's go ahead. This is just a semicolon, so we can ignore that. Let's draw this one out. So selenium and fluorine. We go to the periodic table. Selenium has 6 valence. Fluorine has 7. There's 1 selenium here. There are 4 fluorines. So when you multiply by 4, you got 28. Add the 6, you got 34. And that's your total number of valence electrons, or your magic number. We pretty much know selenium's going to go in the middle, so let's put the fluorines here in the periphery. The next thing you do is you connect everybody to the central atom and give everyone an octet. So right now, each fluorine, let me make this one a little closer so it's not confusing. And notice I'm giving every fluorine an octet. You always do the peripheral ones first. And I don't need to add anything to selenium. It already has an octet. So let's do a quick count here. We got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. We're 2 short. This one has 32. We need to have 34. Whenever you're short, the rule is add the extra electrons to the central atom. So now it matches. We added 2 more electrons, so now we got 34. And if you look carefully, this guy has 5 domains. 1, 2, 3, 4, and here's the 5th. So when you have 5 domains, your electron geometry is trigonal bipyramidal. Okay, so trigonal bipyramidal. And the actual molecular geometry, the shape is there are 4 bonding and 1 non-bonding. We're going to put that right over here. This one is known as seesaw. And the angles for trigonal bipyramidal is usually 90 and 120. So you could put that there. So the molecular geometry, which is the shape, this one would be seesaw. Let's take a look at another one here. So again, ignore the colon here. So we got IBr4. So let's do the valence. I is 7, so is bromine. There's 1 iodine. There's 4 of these guys, so that's 28. And then 28 plus 7. Okay, so we'll go ahead and add that up. So we got 35 here. But remember, we got an extra electron. So we got to add that extra electron. So our magic number really is 36 total valence numbers. Well, we're going to put the let me fix that here. We're going to put iodine in the center here. So we got 36. And then we're going to just surround it with the 4 BRs. Connect them to the middle element. Give all the peripheral elements an octet, which is what we're doing right now. Okay, and if you notice, after I do this, the iodine already has 8. So if we count, there's 8 here, 16, 24, 32, and the magic number is 36. So we're short. We're going to have to add 4 more dots. So we're going to put 1 here and 1 here and another pair over here. And if you look carefully, the electron geometry, because there are 6 domains, is octahedral. And then the molecular geometry, which again, that's the shape over here. Okay, so the actual shape, let me go ahead and do it this way. Out of the 6 domains, 4 are bonding and 2 are non-bonding. If you look back at what we discussed earlier, the name of this shape is known as square planar. That would be the name of this particular shape. And when you have octahedral, the bond angles are 90 degrees. Okay? Let's try this one next. So here we got sulfur, which has 6 valence, carbon with 4, nitrogen with 5. When we add this up, we're looking at 15, but there's a negative here. So add the extra electron. We got 16 in total. Let's put whenever you see carbon, put carbon in the middle. Then you're going to do this. You're going to connect them like this. Give everybody an octet. So we're going to go ahead and do this like this. First, you do the peripheral elements. Then you do the ones in the middle. And when we count here, we want 16. So we got 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We got to get rid of 4 dots this time. We want to go from 20 down to 16. Now this one also has resonance. So you could take away, let's say, 1 from here and 1 from here, and when you do that, this will make a bond over here, and that brings us down to 18. And then if you want, maybe we can take away, just to make even, we can take 1 from here and 1 from here, and we can make a double bond over on this side, and that brings us to 16. And then we're looking at a structure that looks like this, where you have a double bond here, another double bond here. And if you look carefully, there's only 2 domains around the carbon. So the electron geometry for this is going to be linear. Now, both of them are bonding. So the molecular geometry is also going to be linear, which means it has a 180-degree angle. Now, technically, we need to put a bracket here with a negative. Now, one thing that you'll learn, this one, even though this is not the discussion on this video, this one has resonance, okay? This one can also be drawn like this. And I'm going to go ahead and show you the 3 possibilities. Can also be drawn like this, where there's a triple on one side there, okay, and a single on the other. Again, we're going to do this. And then there's a third resonance structure, which I'll go ahead and I'll I'll just draw it here at the bottom since I ran out of room. Remember, the double arrow simply means resonance. And in this example, you have the single bond on this side and you got the triple bond on the other side here. But no matter which one we choose, the shape of all three resonance structures will still be linear, both the electron geometry as well as the molecular geometry. Okay, so this one's going to be linear. And here's our final one. So here we got Sn, which is tin, has 4 valence electrons. So we put 4 there. Chlorine we know has 7. 7 times 4 is 28. And I'm sorry, there's 5 here. I apologize. So let me fix that. Let me go back here. Missed that number there. So that's 35. And then when you add this, it's 39. And then there is and again, that's a colon. There is a negative, so we're going to add an extra electron. So the magic number is 40 electrons. We're going to put 10 in the middle, and then we're going to put the 5 chlorines, 1, 2, 3, 4, 5, just like this. We're going to connect all of them to the center. And we're going to give every chlorine an octet, as you see here. Okay? And then we're going to go ahead and count. So we got 8 over here, 16, 24, 32, and that makes it exactly 40. So this one matches. So this one has 5 domains surrounding the tin. So the electron geometry is with 5 is trigonal, and it's bipyramidal. And the neat thing about this one is that the shape is also going to be trigonal bipyramidal. They both have the same electron and molecular geometry because all 5 are bonding domains. There are no non-bonding. And remember that for this one, the angles can either be 120 or 90 degrees. But the electron geometry and the molecular geometry are both the same. So here's another example. And then here, finally, we have a little chart here that you could take a look at where it just summarizes, based on how many domains. If 2 domains is linear, and this first column here is the electron geometry and the molecular geometry. 3 domains is trigonal planar. The angle is also mentioned there. That one's 120. 4 domains is tetrahedral. 5 domains is trigonal bipyramidal. And then you got 6 domains at octahedral. And then you have all the other breakdowns when there are lone pairs involved. And we went over pretty much most of these. The ones that we went over are indeed the most common ones that you will see. Okay, so this is a good breakdown of VSEPR and the ability to distinguish between the electron geometry versus the molecular geometry. One final note before we conclude the video. Don't forget that this one that we did earlier, remember that after you draw it, I know I put a bunch of circles here and I can remove the circles, but do remember that when you have an ion, to put it in a bracket and put the charge on the corner there. I had forgotten to do that earlier, and with that should conclude our video.